So we're going to do a quick history of the atom and chemistry and such like. So let's start off with the periodic table of elements. The periodic table. Now this is one of the most important inventions or discoveries in all of science. Periodic. Okay. You know, it's pretty impressive when a physicist actually says a chemistry thing is important. Periodic table. So what happened was Mendeleev, back in the day, 1700s, early 1800s, took all of the list of known elements at the time, and it wasn't a complete list. I mean, even now we can't isolate astatine and things like that in Earth's surface very much. And he put them together. And so what he did was he made two tables. So he had one column, and in it, lithium. He put in that column all of the things that reacted the same way. So lithium, sodium, potassium, beryllium, I can't remember all those down here, but down this side we'll have things like fluorine, chlorine, bromine, and we'll have neon, what's the next one, argon, xenon. And he basically made up all these columns, and he made a table. So this way he put down common properties of what they knew, and this way he put down how much the atom weighed per mole. And so they back in the day, so what we got: beryllium, magnesium, calcium, boron, aluminium. But back in the day, when he did it, they didn't know all the elements. Like, they hadn't isolated aluminium. Aluminium hadn't actually been discovered at that point. Nor had helium, for that matter. So that they were missing lots and lots and lots of elements. So he included 66 elements in there, but there were gaps in the table. And he actually left gaps where he thought various things would be. So he was actually making predictions. But they could not explain why these all had the same properties. They couldn't explain why lithium, when you put it in water, goes bang. Sodium, when you put it in water, goes bang. Potassium, when you put it in water, goes bang. Couldn't explain that. Cesium really goes bang. Okay. But they also discovered a few other things, like atomic spectra. So we can tell that this is actually quite important because we actually still use this to this very day. We've just updated it. But we still use that periodic table as the foundation of chemistry. But one thing they noticed is if you took a tube, and we'll actually explain why this happens shortly. If you take a tube of gas and you put an arc through there, put electricity in there, and put a spark through that gas, what that does is it gives off light. And then if you put a diffraction gradient, or I suppose you could use a prism, this will cause the light to diffract out, and you end up... Now, normally, if you did this with white light, you'd end up with a rainbow, but this would give very, very specific bands of light. Very specific frequencies, and I mean, these are incredibly tight frequencies. And so what you ended up with is you'd end up with this spectrum, but it's not complete, it's only in these bright little bands. And every element gives off different bands of light. So these were quite discrete. They'd always give us the same frequencies of light. And it was quite interesting because back in the day, in the 19th century, they were playing around with this, and then they took the spectra of the sun and they ended up with all these lines, and dun 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 dun. They ended up with a whole lot of lines. And they could say, well, we know what this one's hydrogen, these are all hydrogen, that's hydrogen, and this one's lithium, and This one's beryllium. And then they had these lines left over. And they're quite bright lines, and they went, what are these lines? And they said it must be an element that we do not know. So they named it after the sun. They named it after Helios. And so they named that element helium. It was only later that they discovered helium on Earth. So helium was actually discovered in the sun before it was discovered on Earth. I don't know about you, but that impresses me. So these are very clear, very distinct, and they are literally like fingerprints, and we still use this technique to this very day in science, atomic spectra. You heat something up, you zap it, you look at the spectrum lines, how bright they are, and then you can figure out the elemental composition of things. So we still use it. Another one is if you have a tube full of gas, so this is called emission spectra, because it's a spectrum with these lights. But what happens if you have like sunlight? Let's put a big blazy sun there. Let's make it red because I know. I mean, it's one of those common fallacies. People look at and say, what colour is the sun? Most people think it's yellow. And actually the sun's white. The reason it's yellow is because when the sunlight goes through the sky, it scatters out all the blue light. So the white without the blue gives you yellow. So anyway, beside the point. So this light goes through, if we have a tube full of gas, we get a similar thing, except in this case, instead of having we've got our rainbow here, instead of having these light lines, what we end up with is we end up with very distinct black lines. And these are absorption spectra. So what happens is, not only will your gas emit very specific frequencies, it will absorb very specific frequencies. And again, we still use this as a scientific principle nowadays for analysing stuff. And we will actually explain why this happens a bit later on in this chapter. So all the absorption lines are present in the emission spectra. So all of these dark lines will be there, but not all of these lines correspond here. So that's a bit of an interesting point.